All right, we're back with some more discrete probability exercises. We have number 4, 5, and 6 to go. I'll do 4 here. Zoom in a little on the actual sheet, and the rest I'll do on some scrap paper. So we're saying the letters A, B, C, and D are randomly arranged in some order. We want to find the probability of various events here. So the first thing that I want to do is think about the total number of outcomes. Right? If we're randomly arranging 4 letters, how many ways can we do that? Well, this is a permutation, right? It's 4 distinct items that we're arranging, right? Order matters. And so the number of such arrangements, hopefully we remember, well, the first spot, there's 4 possibilities, right? A, B, C, or D. The next spot, there's another 3 possibilities, whatever you didn't choose the first time, and then 2, and then 1. In other words, there's 4 factorial, or 24 different ways that you can arrange any 4 given letters. Okay, so this is our total number of outcomes. This should be our denominator. Now, the first thing it asks is, what is the probability that the first letter in your string is a C? So our favorable outcomes are going to be any string of letters that start with C and end with A, B, and D in some order. So the question is, how many ways can we arrange these last 3 letters A, B, and D? Right? Those would be our favorable outcomes. So, well, we have A, B, or D in the first spot, so there's 3 options here. Whatever you don't choose, you can put in the second spot, so there's 2 options here. And then whatever's left will go in the last spot. There's 1 option for the last spot. So that's going to give us 3 factorial, or 6 favorable outcomes out of our total 24 outcomes that we found before. So this probability is going to be equal to 6 over 24, or 1/4. Okay. For part B, it says, what is the probability that the letters are in alphabetical order? So we need to find our favorable outcomes here, the outcomes where the 4 letters A, B, C, and D appear in alphabetical order. How many ways can they do that? Just 1, right? I mean, the only way that they're in alphabetical order is if they appear first A, then B, then C, then D. If anything's out of place, it's not going to be a favorable outcome because it won't be in alphabetical order. So this time there's only 1 favorable outcome, which means our probability for part B would be 1 out of 24. Now part C is a little bit different because they're saying, what's the probability that the last letter is a D given that the first letter is an A? Right? This, given that a first letter is an A, changes things for us. This is given information. They're saying you already know ahead of time that the first letter is an A, which means our total number of outcomes isn't going to be 24 anymore. If we know the first letter is an A, then the only different possibilities we can have are the number of ways to arrange B, C, and D in the last 3 spots. So just like in part A, there's 3 options for the second spot, 2 for the third spot, and 1 for the last spot. So our total number of outcomes here is 3 factorial, or 6. A favorable outcome would be one in which the last letter is D. So the favorable outcome here is one in which, well, we know that the first letter is A because they already told us, but the last letter would have to be a D. How many outcomes satisfy that the first one is A and the last one is D? Well, the middle 2 spots either have to be BC or CB, right? 2 options here and 1 here, so there's only 2 favorable outcomes. And so this probability would be 2, the favorable outcomes, over 6, the total outcomes, or a 1/3 probability. Okay, so this is problem 4. Let's move on to problem 5. In problem 5, we're rolling 2 normal 6-sided dice. And remember that we've talked about the total number of outcomes when you roll 2 dice. Essentially, there's 6 different possibilities for the first die, right? The numbers 1 through 6, and there's 6 different possibilities for the second die. So in total, there's 36 possible outcomes when you roll 2 dice at the same time. If it helps to think about them as a red die and a blue die, just so that you can keep track of the different possibilities, then you can always think about them that way. right? We want to find the probability that when you roll those two dice, that the sum of the numbers is even. So we need to think about all the different ways you could roll two dice and have the sum of the numbers on the dice be even. I mean, we could list them all. That's one way to do it. We actually might have done that in the warm-up. Oh, we did. We did that in part C of the warm-up. You may recall from number 4C on the warm-up that there were 18 possibilities here. If you don't remember, we could figure it out again by saying, well, they're either going to have to be both even or both odd in order to add up to an even number, right? An even plus an odd would add up to an odd, and that wouldn't be favorable here. So if they're both even, well, the first dice there's 3 options, 2, 4, and 6. The second dice there's 3 options, 2, 4, and 6. So there's 9 outcomes. If they're both odd, again, 3 and 3, because each one could either roll a 1, 3, or a 5. So there's 9 options here for a total of 18 favorable outcomes, right? Or just look back at your notes from before spring break. And so this probability that the sum is even is the number of favorable outcomes, 18, over the total number of outcomes, 36. And this reduces to 1/2. Now part B, I made a little typo on the sheet. What I wrote doesn't really make sense. What it was supposed to say is find the probability that the numbers that you roll are the same, meaning that you roll 2 1s, or you roll 2 2s, or 2 3s, or something like that. So what are the number of favorable outcomes here? Well, I already started listing them. You could roll a 1 and a 1, or a 2 and a 2, 3 and a 3. You could roll a 4 and a 4, 5 and a 5, or a 6 and a 6. These are the only favorable outcomes in this case. And so there's 6 favorable outcomes out of the total 36 that we already found. This reduces to 1/6. And finally, for part C, we want to find the probability that the numbers on the dice are the same, like we saw in part B, or that the sum is even. Okay. So let's think about this here. Just like in the warm-up problem of part 1C, right? This is an or statement, so you might be tempted to add up the previous 2 probabilities or add up 18 plus 6, but the problem is you might be double counting here. And so what we have to do is figure out how many outcomes satisfy that they're the same number or that the sum is even. And we'll do that again using the principle of inclusion and exclusion. First, we'll count the number of outcomes where the numbers are the same. We'll add to that the number of outcomes where the sum is even. And then we'll subtract the case of both. The numbers are the same and the sum is even. Sorry for any disturbances, my cat is knocking things over. Okay, so how many outcomes have the numbers the same? We did that in part B, it's 6. How many of the outcomes satisfy that the sum is even? We did that in part A, there were 18 outcomes there. Now we're going to subtract how many of those satisfy that the numbers are the same and that the sum is even. So how many satisfy both? Well, if we look at all the different ways in which the numbers are the same, right, all those 6 different ways, notice that the sum is definitely going to be even, right? 1 plus 1 is 2, that's even. 2 plus 2 is 4, that's even. 3 plus 3 is 6, right? Any of these, when you add them together, you're going to get double whatever the number is, and therefore the sum is going to be even. So all 6 of these favorable outcomes also happen to satisfy that the sum is even. So we're subtracting 6 here, which means our total number of favorable outcomes by the principle of inclusion and exclusion is 6 plus 18 minus 6, which is just back to 18 again. And so this probability is 18 over 36, which, just like before, is 1/2. So you end up getting the same thing as part A. And that's just because if the numbers are the same, it's already going to satisfy that the sum is even. So adding in this or isn't really changing anything from just looking at the probability that the sum is even. All right, almost done. We'll do number 6 and we'll skip number 7. This time we're going to throw 2 dice again, but we're going to do it 8 times in a row and record the outcome of each of those 8 throws. So the first thing that we want to do is find the probability that the sum on the dice is even all 8 times that you throw the pair of dice. All right, so let's think about all the different possible outcomes here. So we're throwing total outcomes. So you start by throwing a pair of dice. How many outcomes happen that first time you throw them? Well, we did that in the last problem. There's 36 outcomes. Then you take your 2 dice and you throw them again. How many outcomes? It's going to be 36 again. You take your dice and throw them again. Every time you throw them, there's 36 outcomes, which means our total number of outcomes is going to be 36 raised to the 8th power. Now we want to know how many of those outcomes are favorable. So a favorable outcome here would be if you got an even sum the first time, and then you got an even sum the second time, and then you got an even sum the third time, all the way down the line, every single time you got an even sum. Well, how many ways can you do that? There's 18 ways that you could get an even sum the first time, and then another 18 ways the second time, all the way down the line. So there's 18 to the 8 different favorable outcomes here. 18 to the 8 ways that you could get an even sum 8 times in a row. So this probability then would just be the favorable outcomes over the total outcomes. That's 18 to the 8 over 36 to the 8. Finally, for part B, it asks, what's the probability that the sum on the dice is even at least twice? Meaning the sum on the dice could be even all 8 times, but other favorable outcomes would be if the sum on the dice was even 7 times out of 8, or 6 times out of 8, or 5, or 4, or 3, or 2 times out of 8. This is going to do a lot of different if you wanted to do this by cases, it would take a lot of different cases here, because there's a lot of different ways that the sum could be even at least twice, right? 2 or more times. So this is one of those problems where it makes more sense to find the probability that this doesn't happen, right? Find the probability that the sum is not even at least twice, meaning find the probability that the sum is even once or 0 times, and subtract that from 100%, right? Subtract that from 1. Right, so we'll do 1 minus the probability that the sum is even once or 0 times. Right, remember, the reason that we can do this is because one of these 2 things has to happen. Right? When you throw these dice 8 times, it's either going to be the case that the sum was even once, or that the sum was even 0 times, or that the sum was even at least twice. There's a 100% chance that one of those 2 things would happen. And so those 2 probabilities together need to add up to 100%. Right? So what we'll do is just take this easier one to calculate and subtract it from 100%, or probability 1. All right, so our favorable outcomes here, I already see that I'm running out of space. I'm going to grab another piece of paper. Okay, so if we want to find the probability that the sum is even once or 0 times, then we're looking for the number of outcomes where the sum is even exactly once or it's odd every single time. Okay, so exactly once is going to give us, right, let's say that we got an even sum here, but we got an odd sum in all the other spots. And all the other 8 spots. How many ways could that happen? Well, there's 18 ways you could get an even sum, so 18 here, and there's 18 ways to get an odd sum as well. So there's 18 ways to get an odd sum, 18 here, all the way down the line. Okay. Except it doesn't really need to be the case that we got that even sum in the first spot. It could also be that the even sum came in the second spot and every other sum was odd, right? Or maybe the even sum came in the third spot and all the other sums were odd, right? So we actually need to take this 18 to the 8th and multiply it by 10, because that even spot could come in any, oops, sorry, it's not 10, you multiply, my bad, times 8, because there's 8 different spots where you could have chosen to put that single even sum. Okay, so there's 18 to the 8 ways to get a sum that's even exactly once, and to get a sum that's even exactly 0 times means you would have to get an odd sum every single time. Just like before, there's 18 ways to get an odd sum here, 18 here, all the way down the line. Right, and we don't have to multiply by 8 here because we're not choosing one spot to have an even sum. We're saying every single spot has to be odd. So there's 18 to the 8 different outcomes here. And so our total number of outcomes, I'll move back over here, where the sum is even once or 0 times, that would be, let's write our outcomes first. So our favorable outcomes in this case would be 18 to the 8 times 8 plus 18 to the 8. Right? We're using the addition principle here because this is the case where you got exactly one even sum, and this is a case where you got all odd sums. There's no overlap, so you don't have to use principle of inclusion and exclusion. And so now we can go back and say that this probability here would be that sum, 18 to the 8 times 8 plus 18 to the 8, divided by the total number of outcomes, which we already know from before is 36 to the 8. We need to take this whole probability and subtract from 1. That's going to give us the probability that the sum is even at least twice. It's 1 minus the probability that the sum is not even at least twice. Now, there's an equivalent way of doing this that gives you the same answer that uses different cases, and you're welcome to do it that way, but it's kind of a mess. Okay, so hopefully this gets you started on the homework. If you're stuck on things, please reach out to me, let me know how I can help.